Hello friends, so welcome to the 23rd lecture of this course. So as you know, in the last lecture we have discussed the definition of positive definite matrices, and then we have discussed few methods that how to check whether a given matrix is positive definite or not. We have also learned the properties of eigenvalues of positive definite matrices. In this lecture we will extend the same concept and we will see few applications of positive definite matrices, in particular when you are having a positive definite quadratic form. As you know that in the last lecture I have defined a positive definite quadratic form as Q of x equals to x transpose A x, where A is a symmetric matrix of order n and x is a vector from the n dimensional vector space. Now, if this matrix A becomes D, D means we are having a diagonal representation of A, then the corresponding quadratic form, that is x transpose dx, is called diagonal representation of the quadratic form. For example, if you consider x belongs to R3 and A be a 3 by 3 matrix, then if you take A equals to 3 0 0 0 5 0 0 0 1, then the quadratic form Qx, which is given x, x transpose into A into x, which will be x1 x2 x3 multiplied with A 3 0 0 0 5 0 0 0 1 into x vector, then this comes out to be 3 x1 square plus 5 x2 square plus x3 square. So, this particular quadratic form is a diagonal quadratic form. So, I can say in other words that a quadratic form is said to be diagonal quadratic form if there is no cross term or cross product term. So, here my meaning of cross product term means a term something like x1 x2 or x2 x3 or x1 x3. So, all these are having 0 coefficient. So, I can represent this quadratic form basically in this way. So, xtax, so here A is a diagonal matrix. So, I equals to 1 to n aii into xi square, where xi are the components of the vector x. This is another example of the quadratic form. Now, we are having a very important result and we will see the application of this theorem later on. So, that every quadratic form x transpose Ax can be diagonalized by making a change of variable or coordinates, let us say y equals to q transpose x. So, let us see the proof of this. So, proof, let Qx equals to x transpose Ax be a quadratic form. Where A is a symmetric matrix of order n and X is a vector from the n dimensional real vector space. Now, as we know that A is symmetric, so there exists a diagonal matrix D and an orthogonal matrix Q such that A can be written as Q D Q transpose. Means, as we discussed earlier also, if A is a symmetric matrix, it is always diagonalizable, and here the diagonal matrix D will be having the eigenvalues of A as the main diagonal entries, and Q will come from the eigenvectors of A, and those you can write as an orthogonal set of eigenvectors. Now, so if I substitute this form of A in my quadratic form, so I can write X transpose into Q into D into Q transpose into X. Now, define a transformation a vector y which is having the same dimension as of x as Q transpose x. Then y transpose will become x transpose into Q, and this particular quadratic form can be written as y transpose into D into y, which is can be written as sigma I equals to 1 to n dii into yi square, which is a quadratic form, but in diagonal representation. So, this is the result which we have to prove, and this is the proof of this. So, this is the proof which I have done just now. Now, let us take an application of this theorem. So, by diagonalizing the quadratic form q x equals to 13 x 1 square plus 10 x 1 x 2 plus 13 x 2 square, plot the curve q x equals to 72, where x 1 and x 2 are the coordinate axes. So, what curve we need to plot? That is q x equals to 13 x 1 square plus 10 x 1 x 2 plus 13 x 2 square, and this is equals to 72. So, we need to plot this particular curve. Now, q x can be written as x 1 x 2 13 5 5 and 13 into x 1 x 2, and this equals to 72. So, here the matrix A equals to 5, A equals to 13, 5, 5 and 13, which is associated with the quadratic form q x. Now, let us perform the diagonalization of the matrix A. So, here if I calculate the eigenvalue of the matrix A, it comes out to be 13 minus lambda, 5, 5 and 13 minus lambda, and this equals to 0. So, if I solve it, it will be 13 minus lambda whole square minus 25 equals to 0. This gives me eigenvalue as lambda equals to 8 and 18. Now, if I calculate the eigenvector corresponding to eigenvalue lambda equals to 8, then A minus 8I into x equals to 0 gives me 5x1 plus 5x2 equals to 0. The equation from the first row from the matrix A minus 8I and the equation from the second row will be the same, that is 5x1 plus x2 equals to 0. 5x1 plus 5x2 equals to 0. Now, from these two equations I can write x1 equals to minus x2. So, the eigenvector corresponding to lambda equals to 8 can be written as, if I take x1 as 1, so x2 will become minus 1, and if I want to write it as a unit vector, so it will become 1 by root 2 into 1 and minus 1. Similarly, if I calculate the eigenvector corresponding to eigenvalue lambda equals to 18, then it comes out to be 5. So, 18 minus 13 minus 18 will become minus 5x1 plus 5x2 equals to 0, and the second equation will become 5x1 minus 5x2 equals to 0. So, from here I am getting x1 equals to x2, and the corresponding eigenvector will become unit eigenvector 1 by root 2 and 1 by root 2. So, in this way I can write the matrix A as P or Q, where Q is 1 by root 2 minus 1 by root 2, 1 by root 2, 1 by root 2, and the matrix D. So, D will be 8 0 0 18, and then again Q transpose. So, it will become 1 by root 2 minus 1 by root 2, 1 by root 2 and 1 by root 2. Now, the associated quadratic form can be written as Qx equals to x1 x2 and then matrix 1 by root 2 minus 1 by root 2, 1 by root 2 and 1 by root 2, which is my matrix Q. Then I am having matrix D 8 0 0 18, and then I am having Q transpose, which is 1 by root 2 minus 1 by root 2, 1 by root 2 and 1 by root 2 into x1 x2. So, now assume another vector y, which is y1 y2, this equals to 1 by root 2 minus 1 by root 2, 1 by root 2 and 1 by root 2, that is Q transpose into x. So, x is here x1 x2. So, basically my y1 is 1 by root 2 x1 minus 1 by root 2 x2, and y2 is 1 by root 2 x1 plus 1 by root 2 x2. So, in this way I can write the quadratic form 13 x1 square plus 10 x1 x2 plus 13 x2 square 72 in a new variables y1 and y2, and it will become basically 8 y1 square plus 18 y2 square, this equals to 72, or this I can write y1 square upon 9 plus y2 square upon 4 equals to 1, which is an standard equation of the ellipse. Now, if I want to plot this particular curve, so if these are the axes x1 and x2, so then the representation of y1 will be x1 minus x2 equals to 0, or basically x1 equals to x2. Similarly, the representation of y2 is x1 minus x2. By using this now along, so this is my y1, this is my y2. So, my curve will become like this. So, in this way the given curve is an ellipse having this orientation respect to original coordinate axes x1 and x2. So, in this way we can plot any quadratic form by applying the suitable diagonalization and changing the variables. Now, let us see another application of quadratic forms. So, it is not necessary to solve an eigenvalue problem to diagonalize a quadratic form, because when you are performing the diagonalization of the associated quadratic form and the corresponding matrix, you need to calculate eigenvalues and then eigenvectors. So, it will take lot of computation. So, alternative is a congruence transformation C transpose A C, in which C is a non-singular, can be found that will do the same job. For example, by using the LDU factorization, and since here in the quadratic form A is a symmetric matrix, so always we can write this matrix U as L transpose. So, I can write A equals to L D into L transpose, which is a congruence transformation C transpose A C, where L equals to C. Now, the two symmetric matrices A and B are called congruent if there exists an invertible matrix S such that A equals to S transpose B S. For example, here the matrix is A 13 5 5 13 and 8 0 0 18 are congruent, because just now we have seen that there exists a matrix Q which is 1 by root 2 minus 1 by root 2, 1 by root 2 and 1 by root 2, which is A equals to Q D Q transpose, where D is 8 0 0 18 and A is 13 5 5 and 13. Now, my next definition in the same category is inertia. So, how to define an inertia of a real symmetric matrix? So, the inertia of a real symmetric matrix A is defined to be the triplet rho, nu, zeta, in which rho, nu and zeta are the respective number of the positive, negative and 0 eigenvalues. So, inertia of a matrix is a triplet in which first component is the number of positive eigenvalues, the second component is the number of negative eigenvalues and the third component is the number of 0 eigenvalues. counting the algebraic multiplicities. So, if I take this example, so my example is A equals to 1 minus 1 3 minus 1 2 1 3 1 1. So, what is the inertia of this matrix? So, inertia of A can be found just from the eigenvalues of A. So, if I calculate the eigenvalues of A, these comes out to be 4 plus minus root 6. So, if I see here, I am having two positive eigenvalues of A, one is 4, another one is square root 6. So, here rho is 2. So, rho is 2, number of negative eigenvalue is 1 and number of 0 eigenvalue is 0. So, this triplet is the inertia of matrix A. Now, we will see a very important result, that is called Sylvester law of inertia. So, this particular theorem tells us that the two matrices A and B both are real symmetric matrices. The same result hold for the Hermitian matrices also. So, A and B are congruent if and only if A and B have the same inertia. Means A and B are congruent to each other, means you can always find a non-singular matrix C such that C transpose AC equals to B if and only if the number of positive eigenvalues, number of negative eigenvalues and number of 0 eigenvalues for A and B are same. So, in this way we can say the result is enough to check whether two matrices are congruent or not. The alternate statement of this theorem is, suppose D be a diagonal representation of a symmetric matrix A. We say that the index of A is the number of positive entries in D and the signature of A is the number of positive entries in D minus number of negative entries in D. If R be the rank of A, so R will be the number of non-zero entries in the diagonal representation of A, because number of non-zero eigenvalues, then P the index and S as the signature, then S equals to R minus P. So, for example, if you are having a matrix A which is a 4 by 4 real symmetric matrix and eigenvalues of A, let us say you are having 2, minus 1, 3 and 0. Then we will define index of A equals to number of positive eigenvalues or number of positive entries in the diagonal representation of A. Since A is symmetric, so I can always write A equals to Q D Q transpose. So, Q 2 minus 1 3 0 into Q transpose. So, here index of A is the number of positive entries. So, it is 2, signature is number of positive entries minus number of negative entries. So, here I am having 2 positive entries and 1 negative entry. So, 2 minus 1 comes out to be 1, and as I told you, rank of A is index plus signature, and which is the number of non-zero entries in the diagonal representation of the matrix A. So, again The Sylvester law of inertia can be defined like this: the two matrices, two symmetric matrices A and B are congruent if and only if their diagonal representations have the same rank, index and signature. So, this is the alternate definition or alternate statement I will write. So, let us consider an example of this. So, determine which of the following matrices are congruent to each other. So, all the three matrices are given where the matrix A is 1 minus 1 3 minus 1 2 1 3 1 1. The matrix B is 1 2 1 2 3 2 and 1 2 1, and C is having first row as 1 0 1 0 1 2 and 1 2 1. So, if I calculate the eigenvalues of matrix A, so eigenvalues of matrix A comes out to be 4 root 6 and minus root 6. The eigenvalue of matrix B is 0, 5 plus square root 33 by 2 and 5 minus square root 33 by 2. And the eigenvalues of the matrix C are 1, 1 plus root 5 and 1 minus root 5. Now, if I talk about the rank, index and signature of these three matrices, so the rank of matrix A is the number of non-zero entries in the diagonal representation of A, and which will be 3, because the diagonal representation will contain the eigenvalues. The index will be the number of positive eigenvalues or positive entries in D, and the signature is number of positive entries minus number of negative entries. So, 2 minus 1 1. For this matrix the rank is 2 because one of the entry is 0, index is 1 because only 5 plus root 33 by 2 is the positive entry, and signature is 1 minus 1 0. For this matrix again I am having rank 3, index as 2 and signature is 1. So, if you see here the matrix A and matrix C are having the same rank, index and signature. So, A and C are congruent. A equals to P C P transpose by using either LDU factorization. So, if you go by the earlier statement of this Sylvester law of inertia, so there I need to calculate rho, nu and zeta. So, rho is defined as the number of positive eigenvalues. So, here it is 2, nu is the number of negative eigenvalues which is 1, and zeta is the number of 0 eigenvalues. So, 0, here it will be 1 1 and 1, and the third one will become 2 1. So, again A and C are having the same inertia, because for A this is 2 1 1, which is same for C. So, again A and C are congruent to each other. In the same way, we can have a diagonal form or quadratic form. So, consider the quadratic form f x equals to 2 x 1 square plus 2 x 2 square plus x 3 square minus 2 x 1 x 2 minus 2 x 2 x 3. So, find a symmetric matrix A so that f x equals to x transpose A x. So, here q x given as, so solution q x given as 2 x 1 square plus 2 x 2 square plus x 3 square minus 2 x 1 x 2 minus 2 x 2 x 3. So, now I can the associated matrix is q x equals to x t A x, then A equals to, so here will come the coefficient of x 1 square 2, the second diagonal means diagonal entry in second row will be the coefficient of x 2 square, and in the same way diagonal entry in the third row will be the coefficient of x 3 square minus 2 x 1 x 2. So, I will take minus 1 here and minus 1 here, minus 2 x 2 x 3. So, I will take minus 1 here and minus 1 here at 2 3 or 3 2 entries, and these are 0. So, this is the associated form. Now, if I see the eigenvalues of this matrix, the eigenvalues of this comes out to be 0.1981, 1.555 and 3.2470. So, here if I calculate the inertia of this, inertia will be 300. Here rank is 3, index is 3 and signature is again 3. So, in this way, since all the eigenvalues are positive, so I can say, and if rank equals to index equals to signature, then I will say the matrix is positive definite PD, and hence the associated quadratic form is also positive definite. I will ask you to work out on this and find out a suitable transformation y equals to q transpose x such that q x you can write as y t d y, means the corresponding diagonal representation of the quadratic form, and from you will see the entries of d will be 0.1981, 1.555 and 3.2470. So, with this I will end this lecture. So, in this lecture we have seen a couple of applications of the quadratic form. These are the references. Thank you very much.